one technique that I have found to be both very fun and effective as I learn or study new things is to put myself and ourselves in the mind of the device. Whether it's a layer 2 switch, what am I going to do? Or whether it's a router or a firewall or some other device. And that's going to help us better understand it. So to that end, here's what I propose that you and I do in this video is you take a look at OSPF cost. Let's draw out a topology together. And then as part of that, let's think, okay, what path would we choose and why? And also, as we add more layers and more information, that's going to help us be better at configuring, verifying, and troubleshooting the routing protocol called OSPF when it comes up. So let's begin with a simple 4-router topology. So these represent routers. We'll call this guy router 1, router 2, router 3, and any guesses? Yeah, router 4. Awesome. And let's imagine that each of these routers is connected off to a local segment where there's switches and users and so forth. And let's put a little line there to represent there's a network out there. And then we have some interconnections. And we'll just make this pretty straightforward. Boom, 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 boom. Like that, just like that. And then let's add a connection between R2 and R3 just for maybe a little fault tolerance. So my question is this. If you and I were sitting here, say this is the PC, and let's imagine the PC had a default gateway correctly configured that would use this interface on R3. And if we're trying to get to a server, let's label that here. My question is, which path, if a PC forwards a packet in to the routed environment here, which path should R3 use to forward it to the server? Now, I have heard before, more than once, that the fastest path between 2 points is a straight line. However, we need to kind of flip that paradigm a little bit because not all interfaces are created equal in a network. We might have very slow serial interfaces. We might have moderately slow fast Ethernet interfaces that are at 100 megabits per second. We may have faster interfaces that operate at gigabit speeds and then beyond. So we have to make sure that we're taking the best path based on all the data. So let's go take a closer look at this topology and add some more of that information so we can make an informed decision on which is the best path between the PC and the server. So I would agree that if all these links, all these straight lines represent gigabit Ethernet all the way around, that the fastest path would be, R3 to R4, no problem. But if we start adding information like these links here are gigabit speed, and link between 1 and 2 is gigabit, and between 2 and 4 is gigabit, and I dreamed about this last night, by the way. I was thinking, okay, how can I make this effective and make sure it's fun and people really get it? And this is the topology that I finally came up with. I didn't dream the whole topology. I kind of had the idea in the dream, but it panned out to be this. Let's imagine this link between R3 and R4 is fast Ethernet. So this is 100 megabits per second, and this is 1,000 megabits per second. So the gigabit is 10 times faster than the fast Ethernet. Now, if we wanted to forward a packet from this PC over to the server, which is the best path? To go over the 100 megabit connection or to go around the horn here, which is all gigabit. So let's talk about how distance vector with RIP, for example, would handle it. A distance vector routing protocol would say, oh, it's just one hop using this path here over fast Ethernet, which wouldn't be the most efficient path. And that's why we don't use RIP too much anymore. We're going to use link state routing protocols. And let me put the cost in yellow. Let's imagine that this interface right here on router 3 that goes up to R1 has a cost of 1. So the costs are in yellow. And the cost from router 1 going over to router 2 is a cost of 1. And the cost from router 2 over this interface going to router 4 is a cost of 1. And then the cost here on router 4 to get to this network is also a cost of 1. So we're looking at all the outbound paths. That's the costs that OSPF is going to add up to determine the best path based on the least or lowest cost. And it will consider that the shortest path. And then for this fast Ethernet, if we put the egress interface, egress is a fancy word for saying the outbound traffic on an interface. So if this is a value of 10, then OSPF could do the calculation and say, well, if I take this path, I'll put it in green. Brr, 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 brr. Let's figure out what the cost would be. We just add up all the exit interfaces in that path. So that'd be 1 here, 2 here, 3, and 4. So the cost on this path would be 4. And now let's pretend we're still the OSPF router, router 3, and let's calculate the cost if we want to forward a packet over this bottom path right here. So what would that be? I'm asking you to think about that for a moment. What would the total cost be from an OSPF perspective And if you're saying, well, Keith, we'd add up all the exit interfaces and their costs, which would be absolutely right. So we have 10 here, plus we have 1 here. So the cost on this bottom path would be a total cost of 11. So my question for you, if you and I were a smart OSPF router and we're looking for the shortest path first and use that for our routing table, which path would we use? Path A, a cost of 4, or path B, a cost of 11? And the answer is we're going, and that's how OSPF works. And I've got a follow-up question for you. And the question is how? What do you mean, Keith, how? Well, how did R3, right here, how did he know that R2 on this interface had a cost of 1? And how did he know about R1 that on this interface had the cost of 1? And so forth and so on. And the answer is what? What in OSPF is used? I mentioned it briefly in the previous video, but do you recall what is the thing that is advertised to every router in this area that allows router 3 to have that personal knowledge of the links that are involved on router 1 and their cost, and the links that are involved on router 2 and their cost, and the links that are involved on router 4 and their cost? And if you're saying, Keith, I believe it was a link state advertisement, that is exactly right. And because those link state advertisements are propagated through the area, and all these routers in this example are in the same OSPF area, that's why R3 had all the data. It put all those LSAs in what's called a link state database. It's a fancy way for saying all the information about what's going on the network, and it used that information then to calculate the lowest cost, or the shortest path first, to get from here, from itself, to the destination network. And let's do one more for good measure to make sure we all have it. So let's imagine here we have router 1, and it's got connectivity to router 2 and to router 3, and we'll go for a couple more. So there's router 4, router 5, and then we have a final destination network that we're trying to reach. Here's the goal. And we might have a user like this over here. Maybe it's Bob at his PC using R1 as a default gateway. And I'm going to put the costs on all these interfaces so that we can make our best decision regarding which path is going to be used. So I'm going to put a cost of 4 here on this interface, a cost of 5, cost of 2, cost of 3, 1, 6, 2, 3, 8, 9, 2, and that's it. So with all those costs involved, for R1 to make a forwarding decision over here to the goal, which path would it use? That's my question. Would it use path A, the top road, or would it use path B? And I'm going to give you a few seconds to do that math, to think about it, just like you would if you're an OSPF router. And then when we come back, we'll review our answers together. So the wrinkle that I surgically injected into this diagram is that I included the interface cost, the link cost, on both sides. So R2 has 2 interfaces. Each interface is going to have an associated cost. And the point I wanted to drive home is that when we're calculating the shortest path, we're calculating it in one direction. In this example, it's going from here to here. So all we're looking at is egress, or exit interfaces. So we would be using the calculations with 5 and 2, with 6 and 2, with 9 and 2. And all the others are just distractors. Those inbound interfaces don't count for the calculation. So on the top path, path A, it'd be 9 plus 6 is 15, plus 5 more is 20. That'd be the cost for the top path. And for the bottom, it'd be 2 plus 2 plus 2. I can do that one. That's 6. And so OSPF would choose this bottom path as the routes that would be taken, from, at least from R1's perspective, as it forwards packets in the direction of the goal. And the reason that R1 knows about all those details is from those beautiful link state advertisements that are being sent by every router, and the collection of those in the link state database, which R1 is using to do the calculations and make its decision on which path is literally the shortest one. Hence, open shortest path first. So in this video, we played the role of the router in making a decision on which path to take based on outbound interfaces and the cost. And just like a bargain shopper, we want to choose the least cost every time to get the best path to the destination. So thanks for having some fun with me and playing along and thinking like the router as we continue our discussion in OSPF, and I'll see you in the very next video. Meanwhile, I hope this has been informative, and I'd like to thank you for viewing.